Welcome class to chapters 20, 21, and 22. We are going to talk about hailstorms, lightning, and downbursts, otherwise known as microbursts. I decided to put these three chapters together because they're all related to various thunderstorm hazards. What you see in the background is actually my backyard several years ago when we had a thunderstorm. We actually had a thunderstorm in the wintertime, and so some people thought maybe this was sleet, but technically it was very small hail. So here are some of the questions we're going to answer. What the difference is between graupel and hail. You might not have heard of graupel, but it's in a very important part of the hailstone formation process. How does actual hail form? What causes lightning and thunder? We might talk more about the lightning than the thunder, and there's still some debate on the exact causes of lightning and thunder. There are different stages of a lightning stroke, which is kind of interesting. Each time, you might not actually see lightning like the lightning bolt when we have lightning around here in California, but often in other parts of the world you will see the lightning bolt itself, which we call the lightning stroke, and it's actually made up of several stages. And then we're going to talk about downbursts or microbursts and why they're very important to understand, especially for aircraft safety. Here's a list of some of the terminology we're going to get into. We've already talked a little bit about graupel and hail, thunder. A step leader and dart leader are different stages of a lightning bolt. Sprites are very interesting and pretty relatively new phenomena that we discovered, I think maybe back in the 1980s, and we still don't know a lot about them. And then talk a little bit about microbursts, downbursts, and what Doppler Radar can do to help us. Okay, so like I said before, is this graupel or this is hail? It looks like graupel because graupel is the same size as this hail that you're looking at, but because there was a convective thunderstorm nearby, the meteorologists, and with my assessment, have decided that it was actually hail. While most hail is relatively small, some hail can get very large. This hailstone has a circumference of 7 inches. This, I believe, is still the world record for hailstone. This hailstone has a diameter of 8 inches. Imagine this falling on top of you, especially if you hit your head. While fatalities from hail are rare, they do happen. And to give you sort of a comparison, you see over here in the bottom right, basically, I think that's just a marble, and then we have a golf ball, a tennis ball, a baseball, all the way up to a grapefruit, and then we have the actual hailstone. So this just gives you a better idea of how large this actually was. Most hail must, at least these large hail stones, you have to have some kind of colder weather. You don't see this a lot in the tropics, but you do see them in the mid-latitudes toward the upper to mid-latitudes. This just gives you another frame of reference. Man, that is really large. And you got to check out some of the videos that I posted on Canvas about some very destructive but awesome hailstorms. If you cut into a hailstone, you will see these sort of rings, like they are like tree rings, and that's because when hail actually forms, it forms in an iterative process where you have more and more supercooled water, perhaps other ice that are forming and creating these rings. So you get layers and layers of ice that are formed. And it's when it's too heavy for it to be sustained in a cloud, that's when it actually falls out, and it could be a couple of hailstones, or it could be an actual hailstorm where you get a lot of hailstones. So unfortunately, hail can be very damaging. One of the things that I always worry about if we're going to get hail is my car. I have a garage, but I don't park my car in the garage. I can't actually fit it in my garage, and so it's exposed outside. And in fact, last spring we had a small hailstorm. I was in Encino, but I was driving about 40 miles per hour and it was extremely loud, and I thought for sure that my car was going to be dented up, but thankfully it wasn't. So again, Graupel, they're just tiny ice particles, and your textbook talks a little bit more about what Graupel is. It's kind of like soft ice, and the diameter is only 1 to maybe a few millimeters, and it has a consistency of a snowball. Hail, on the other hand, grows from the Graupel and mostly comes out of an intense thunderstorm, especially with strong updrafts. That's why regular thunderstorms don't necessarily form hail, but intense supercell or multicell thunderstorms can actually have an updraft that suspends some of these ice crystals or supercooled water droplets in the cloud for a longer time and allows these ice particles to grow very large and to form hail. This is a very simple drawing. This is not a drawing that comes from your textbook, but a very simple way to think about how hail forms. If you have a very strong updraft, and that strong updraft suspends a piece of ice, let's say a piece of Graupel, and it goes up and down inside the cloud. And it's the updraft is too heavy for that ice crystal, Graupel / hail, to actually fall out of the cloud. So the longer it's in the cloud, the more layers of ice grows on it, potentially, because as you're moving through the cloud, you're getting bombarded by more and more ice and supercooled water. Now, eventually, that ice particle will either get too large and will fall, or what makes hailstorms is it falls into the downdraft where you have other precipitation, and then you can get this hail shower where you just get a lot of hail. Hail shower, hailstorm, they're basically the same thing. This figure comes out of your textbook, at least the 3rd edition of the textbook, and it talks a little bit more specifically on how hail forms. So there are studies out there using Doppler Radar that shows that Graupel can serve as hail embryos for very large hailstones, and they're believed to enter the updraft along the edge or the periphery of the hook echo. So where you see this large hail trajectory is actually, it starts on the, if you think of this technically is called the bounded weak echo region. It's something that you would see on a Doppler radar. But essentially that's where the updraft would be, where a tornado would be. So if it's on the edge of that area, it can get, for lack of a better term, get drawn in or sucked up into the updraft, and some of it might just go out into the anvil part. But the large trajectory, then, it can only go up there for so long, and it's in there in a pretty chaotic fashion. So these particles grow within the updraft, and they spiral upward within the rotating mesocyclone. While it's floating up there, these stones can actually get up to 2 inches or even larger, as you saw. And then eventually, when it goes a little bit to the northeast and it's out of that updraft, it can fall down as a hail cascade, which again is another way of saying a hailstorm. If we're looking at it from the top as a map view, you can see that same trajectory right here for very large hail. So as a rule of thumb, this doesn't always happen, but as a rule of thumb, as a severe thunderstorm forms, let's say in the Midwest, the hail tends to be to the northeast, just to the northeast of the tornado. So if you have storm chasers and they end up in a hailstorm, they probably, and there is a tornado, they're not very far from the tornado. So that's sort of one indication that you have a tornado, or at least a very strong and severe thunderstorm. Okay, so as you've noticed, a lot of these chapters in the book are quite short. So we're going to go ahead and talk about lightning and a little bit about thunder. So everyone, has these ideas of what lightning is, and hopefully everyone in this class has at least heard thunder, if not have seen a cloud brighten up by lightning, or even better, a lightning bolt. A lightning bolt is very interesting, and it's very, very short, but we'll talk about this a little bit later. But also one of the most interesting parts about lightning is what happens to people. Believe it or not, most people survive lightning strikes. Not undamaged, however, but they do survive. So basically, lightning is just a discharge of static electricity. It's just a huge version of when you get zapped as you're walking across, let's say, a carpeted room when it's dry outside and you hit something that's metal. You touch something that's metal. So it's a discharge of electricity. And when we have thunderstorms, we have a lot of different particles in the cloud, like we just talked about with hail and graupel. We also have sometimes ice crystals, and that helps distribute some of that charge and separate the charge. So lightning basically can happen within a cloud, which is the most common type, thankfully. It can go from cloud to cloud, and then it can go from cloud to ground or from ground to cloud. Thunder is basically a result of heat actually being and warming up the air to an amazing amount of temperature. So a lightning bolt can be 5 times hotter than the surface of the sun. So when you have that sudden heating of a very thin column of air, it expands very quickly, and that is thought to be responsible for thunder. And like I said, graupel, hail, supercooled water, and ice crystals all play a part in producing a strong enough electrical field to produce lightning. Believe it or not, we have an electrical field, even when it's not storming outside. So a fair weather electrical field is about like 100 volts per meter or so, where we need 1,000,000 volts per meter to get a lightning strike. So we're not going to get lightning with a fair weather electrical field. So what happens is that a thunderstorm will disrupt this fair weather electrical field. Okay, so let's keep it simple first. What usually happens, and I'm going to go over the process of how this happens, but what usually happens is that a hailstone will have a negative charge, and the colder ice crystal will become positively charged. And then when you're in an updraft, the hailstone, because it's heavier, will tend to hang out closer to the bottom of the cloud, where the ice crystal will be located at the top of the cloud, and this is just one way. Now you might think, well, this is just one hailstone and one ice crystal. Having a negative and positive charge, what's the big deal? These are just very small particles. There are billions of these particles in a thunderstorm, and so when you have enough of them separated, you can get a very strong electrical field. Okay, so let's magnify a little bit the interaction between hail and ice crystals. So we call this interface charging, and it occurs when ice crystals grow by something called vapor diffusion. Okay, so the surface distribution of the electrons is actually different in the two ice particles, as you see there, leading to a transfer of electrons. And so if you look at A, you look closely there, let's see, you count, let's do the hailstone. We count 1, 2, 3, 4 negative ions, and 1, 2, 3, 4 positive ions. But the ice crystal has 3, oh, actually no, it does have 4 and 4, but notice how it's distributed a little bit differently. And so if you look at B, one of the electrons will actually transfer to the hailstone. So C is the result, and now the hailstone is more negatively charged, and the ice crystal is more positively charged. You can actually count. So in C you have 1, 2, 3, 4, 5 negative ions, where you only have 4 positive ions. The the ice crystal has 3 negative ions and 4 positive ions. Okay, this is another way to look at it. This is something called induction charging, which occurs as charge is transferred basically between the large and small ice particles. And it basically happens during this strong electrical field. So the smaller ice particles, they obtain positive charge and the hail will obtain the negative charge. But the smaller particles are swept upward by the updraft while the larger particles are hanging out closer to the bottom. This is the way we can get a very strong electrical field and therefore lightning. And this is a little bit more of a detailed view of that distribution. Now this is just your textbook distribution of a thunderstorm. And if we happen to have a lot of negative charged particles at the bottom of the cloud, which we do, and we happen to be above an area that is more positively charged, then you can see how we can actually get a lightning bolt between the cloud and the ground. But most of the time lightning is happening within the cloud, which again is a very good thing. One other kind of interesting phenomenon, most of the lightning might fall here. Every once in a while you might have lightning coming from the very top of the cloud and reach all the way to the ground. Sometimes we think of those as being very, very strong lightning bolts. Sometimes they're called bolts out of the blue, which is unfortunately one of the reasons why some people get struck by lightning. Okay, so it's not just one lightning bolt. There are actual stages of a lightning stroke. So if you look at A, we're looking at negative charges, and what they do is they basically look for the path of least resistance. And what that does is that creates a step leader. So you see here that there are this is a millisecond. You would only be able to see this if you were just so lucky to be able to capture these exact moments of these stages. So you have a step leader, doesn't make it all the way to the ground. Okay, and then a powerful return stroke will develop when the traveling spark of a positive charge surges upward to meet the step leader. So you have your lightning bolt, and then it can actually go back. It hits the ground and can go back. That's one way. And then a second surge of negative charges can descend along that already ionized path from that previous stroke, and we call that a dart leader. And then we have a second return stroke. And so there are multiple stages, and you might have seen this. If you've ever seen a lightning bolt hit the ground, it looks like it flashes a couple times. That's because it's not just one bolt, it's several bolts. There's that positive polarity stroke, which I was talking about earlier, bolt out of the blue. Those tend to be much stronger lightning strikes than the ones coming from the bottom of the cloud. I love this picture. It's a little old, but it really paints a great picture of how lightning can go from one part of the cloud to the other. It can stay within the cloud, or more ominously, it can go from cloud to ground, or even from ground to cloud. Okay, now these are relatively rare phenomena, and we don't really know much about them. There are sprites, elves, and blue jets as well, and these are things that have only been photographed a couple of times, and they're not understood very well. But what we know, these are basically electrical phenomena coming from the top of these clouds, and I believe I'm going to post a video that talks a lot more about them, and they talk about this in your book as well. So basically, sprites and elves are triggered by these cloud to ground positive polarity strokes in the anvil region, and so these things can develop above the anvil. And blue jets develop over the region where the most convection is occurring. You can see this, and this has been observed from space. It's actually easier to see them from space than it is from the ground. So where is lightning? As you probably know, lightning doesn't occur much around here. In fact, we might see an average of 5 to 10 days of lightning, and that's mostly in the mountains, not here in Los Angeles near the coast. Within our country, Florida has, in some places, Florida has more than 100 days of lightning. That's about 1/3 of the year. And if you don't like lightning, you do not want to go to tropical regions. Tropical regions often have lightning as well, in areas, especially the tropical regions over land. If you see here in Central Africa, we have quite a bit of lightning. This is something you don't want to happen. So lighting safety is a big deal. Back in July of 2014, somebody was killed by lightning here in Los Angeles. This person was on Venice Beach. And one of the reasons is, first, this person was at the beach, and so it's not the best place to be when it's lightning out. Also, we don't get a lot of lightning in the summer. And with that, nobody really expected it. So there's a lot of rules on what not to do when it's lightning. You basically don't want to be outside. If you're outside, don't be next to a tall tree. Don't carry a metal object. When you're inside, some of the things that I learned when I was a kid, you don't want to take a bath or use the plumbing. And you don't also want to use a corded phone. People have gotten struck by lightning. Now this person, if this person is in the very beginning stage of a lightning strike, so if I were this person, I would run to shelter as quickly as I could. But like I said earlier, most people actually survive lightning strikes, and we don't really know why. However, they can be badly damaged both mentally and physically. You can Google the name Linda Cooper. Linda Cooper has been struck by lightning 3 times. And I used to play a video when I taught this in the classroom. So the first time Linda Cooper got struck by lightning, it damaged most of her brain. And she couldn't even remember how to add, subtract, multiply, and divide. She had to go back and get her GED with GED students in order to learn all that again. And then I think the second time she said that she thought she had the flu for like a year. So you do not want to get struck by lightning, even if the chances of surviving are relatively good. Okay, so our next topic is the downburst or microburst. I want to make sure you understand that this is different from a downdraft that you can get from just any kind of thunderstorm. These downbursts and microbursts can flow at speeds over 100 miles per hour, and there are certain environmental conditions that are favorable for these downbursts and microbursts. To keep it really simple, again, we'll start pretty simple. One of the ways we can get these intense downbursts is we can get a lot of precipitation here under the cloud that's evaporating. So if we go way back to a beginning lecture, evaporation is a cooling process and it consumes latent heat, so it makes the air colder, which is more dense. There's also this concept of precipitation drag, which can actually pull the air down even more. So those are the sort of the larger scale environmental conditions that we need for a downburst. Basically, okay, so a downburst sometimes is called a microburst if it's very small. So evaporation is one of the processes, and this drag of the precipitation can induce these downbursts. So to be more specific, we need a large environmental lapse rate. Basically, the environmental lapse rate has to be large enough so that these parcels here are always colder than the environment. So remember, when we were thinking about air going up, we wanted air to go, when air goes up, it has to be warmer than its environment. But now we're talking about air going down. And for it to go down and go all the way down to the ground, it has to be, the environmental lapse rate has to be very, very high, so that these parcels inside the downburst are actually colder than the environment. Also, in addition to that, we need dry air. Okay, remember, we need really dry air so that it can evaporate. However, a slight increase in the air's moisture near the surface could actually keep it makes the moist air less dense, and so that dry air that is interacting with the moist air will fall to the ground even faster. And you still have to have these below freezing temperatures in much of the cloud, because we get a sort of a mixture of ice particles, which when they melt can actually lead to further cooling. So how do they look? Well, it's not just one, it's not like a hose where you just have one major piece of air falling and then just cleanly radiating outward. There's actually multiple downflows, we'll call them, and they create these sort of stretching vortices, these vortex rings, and there could be multiple rings, and we know this because we've looked at damage. Damage from a microburst can actually look quite like a tornado at first, until you really dig deeper and notice that tornadoes don't make nice, neat radial patterns of damage. It's much more chaotic. This gives you sort of an idea of how these rolls can actually hit the ground and then go back up and spiral a little bit. You do not want to be in one of these downbursts or microbursts, especially if you're in an airplane. So this is the reason why we care about these. First of all, back before the 1970s, we really didn't know much about them, and we didn't know how to detect them. These days, thankfully, we have technology that will detect them, but there were, unfortunately, airplane disasters because of these microbursts. And there are different kinds of microbursts, but we're just going to talk a little bit about just the basic kind that just go down and then radiate outward. So why is it a problem for airplanes? Airplanes, believe it or not, a lot of people think airplanes actually, they actually rise because there's less pressure above the wing and much greater pressure below the wing. Well, there is less pressure above the wing and there is greater pressure below the wing, but that's not enough to make them lift. If you ever notice, an airplane wing is tilted just ever so slightly so that when air moves over the wing, it goes downward. And so when you have air going down, and it's a lot of air, the faster that airplane's moving, the faster the air is going down. That's just using Newton's third law. Every action has an opposite and equal reaction. So the bottom line is you need sufficient airspeed to stay in the air, basically. And when you encounter a microburst, what happens is you can unfortunately think that you're going a lot faster than you really are. Airplanes must land, or I should say either land or take off into the wind, because it's that headwind that makes them lift off the ground. So if you take a look at this first diagram here, the airplane is taking off in a headwind, unfortunately, and it's making it lift, and it thinks that the airplane is going faster. So it may actually start to decrease the airplane speed to the point where you're below what's called like the stall rate, where the airplane would actually not be controllable. So the airplane's going up and up, and then of course when you get on the other side, you do not want a tailwind. Tailwinds make airplanes go down, and so you do not want a tailwind, and unfortunately eventually you get into that tailwind. This is why this is devastating. What about if you're trying to land? If that microburst is in front of the runway, you might actually, when you're starting to land, you might actually go higher into the air, and you think, okay, well then I need to stall. I need to slow down the airplane. But then of course, unfortunately, you're on the other side and you have a tailwind. Tailwind, once again, will not help you keep control of the airplane, and then the airplane will crash. So these days, a lot of different modern technology has been put into trying to detect these microbursts. And actually, using the terminal Doppler radar system, we use basically the same kind of technology that we use for tornadoes. Oh, here's another thing. So, downbursts don't just increase the headwind or increase the tailwind, it can actually increase the crosswind, which can also drift the airplane either to right or left and cause issues. Unfortunately, with trying to land or even trying to take off. So one of the ways that we use Doppler radar to figure out microbursts is we look at an area that has a wind direction that is almost the exact opposite to an area next to them. So what we're looking at here is a schematic depiction of a downburst in a radial velocity field, and this is the terminal Doppler weather radar system. When you have divergent velocities, what you will see is you'll have, let's say the red, okay, means that wind is going to the west, let's just say, but the blue means that the wind is going to the east. When you have an exact opposite wind field like that right next to each other, you have some kind of either rotation, or you have, in a tornado, or you have this microburst because they have winds of different directions, opposite directions right next to each other. So we're going to get into tornadoes, hurricanes, and El Nino, La Nina in the next unit. So I hope now you just have some basic understanding of thunderstorms, which will help you understand the last unit. Thank you. See you next time.